Find the area between the curves f of x equals 1 minus x over x squared plus 1 and g of x equals 1 plus x over x squared plus 1. X goes from 0 to 1. It's the shaded area below. So it's what you see in the picture. We have some options: log of 1, log of 2, log of 3, log of 4, and log of 5. The answer is? And you're probably thinking, there's x squared plus 1's down there, Steve. Where's your pi's? Where's your arctangents? I'm very disappointed. Do we have a guess? B, log of 2. Excellent guess. All right, so it didn't explicitly tell us which functions are on top and which are on the bottom, but we can figure that out pretty quickly. For example, at x equals 1, you'll get 2 over 2, which is 1 here, but you get 0 over 2, which is 0. So the 1 plus x over x squared plus 1 is the top. 1 minus x over x squared plus 1 is the bottom. If you're looking for area, integrate from start to stop, 0 to 1, top minus bottom. There's no crossing, so we don't have to do any like, oh, find where they cross and split into parts. Well, when we subtract, same denominator, whew, good. The 1's cancel. X subtract minus x makes 2x, and that looks nice. We see downstairs x squared plus 1. If we take the derivative of that, we get the upstairs to 2x, which makes it a du over u, a log. In general, if you ever see the following, if you see a function downstairs and you see the derivative of function upstairs, then it's like, this is a log. And so in this case, we get log of u. It's a definite integral, so we don't actually have to say log of x squared plus 1. We always go forward in definite integrals. We never have to go back. We just have to make sure to update the bounds. So our original bounds were 0 and 1. These are our x bounds. So this is x equals 0, x equals 1. We have to update to u bounds. U equals 1, u equals 2. And the way you get those, plug it into the relationship. When x equals 0, 0 squared plus 1 is 1. When x equals 1, 1 squared plus 1 is 2. So we end up with log of u evaluated from 1 to 2. Log of 2 subtract log of 1. Log of 1 is 0. So our final answer is log of 2. All right. Good. Any questions on that one? Okay. Well, going into our exam, a thought. Our last thought, actually, because this is our last lecture. From here on out, it's all review. So it always seems impossible until it's done. And I think a lot of people, and I know this is true for myself, I get frustrated and I'm like, I'll never be able to make this work. It'll never happen. And then all of a sudden it happens. I'm like, what? This is so much easier than I expected. Or maybe a better way to say it, and it's not just about me. I know this sounds really, I'm better than I thought. And I think that's true about you. You're better than you think you are. And problems may seem impossible, but you can do them. Practice. Practice. You can get it. All right. So, well, don't worry. If you continue on in Calc 2 next semester, more thoughts are coming. All right. So what's today's topic? Well, we're going to talk about differential equations. Now, that sounds like a complicated subject, and it kind of is. If you look in course catalogs, you'll notice, for example, there's a course called Differential Equations, which is 2670 in our catalog. But there's actually about 3 or 4 courses with the title Differential Equations in them. So there's lots and lots to be said. Well, what is a differential equation? Well, the name kind of gives it away. It's an equation. Well, what's an equation? there's something with an equal sign. So something equals something. That's an equation. Well, what's a differential? A differential is just another way of saying a derivative. So it says, okay, I want an equation. There's an equal sign. I want a derivative involved. That's a differential equation. So anytime you have an equation with a derivative, you have a differential equation. Now, what's the goal? Well, the goal is to recover the function. So essentially, we have information about its derivative. What's the function? And let's start with a fun example, Hooke's law. Does anybody remember Hooke's law? I'll give you a hint. It has to do with a spring. Hooke's law. It's a physics type thing. So, what does Hooke's law say?
Is it with the elasticity, like how far it'll go before it gets back with the amount of force? Does it stretch?
Well, so the idea of Hooke's law says, if I have a spring and I stretch it, what does the spring want to do? It wants to go back. Now the question is, how badly does it want to go back? If you stretch it a little bit, it's like, I'll pull up a little bit, but I'm not going to pull very hard. If you stretch it a lot of bit, it'll be like, and push really hard to go back up. So, Hooke's law says that if you have a spring, so imagine that you have a spring. So here's our spring. So there's sort of a resting state. Now, you stretch it. What's going to happen? Well, the spring is going to want to go back up to where it started. And it's reflected in the amount of force. And it says the force is proportional to is just a fancy way of saying there's a constant, how far you've pulled it. And it's usually written as minus x. So x is how far you've pulled it away from your resting state. Now, why a minus sign? If I pull down, which way does it want to pull? Up. If I push it up, what does it want to do? Go back down. So the force is the opposite of how you've pulled it. So that's why there's a minus sign. So that's Hooke's law. Seems pretty simple. And it feels like, yeah, you pull a spring, it wants to go back. All right, now, let's keep testing your knowledge. What is force? How do you find force?
Mass times acceleration.
Mass times acceleration. Okay. Now, mass, we don't have a better name for it. That's m. But acceleration, we do have a name for it. So x is position. How does acceleration relate to position? Second derivative. Yeah. So this becomes mx double prime equals minus kx. Or it says x double prime is some constant minus alpha times x. Now I don't know what alpha is. Now what is this? It's an equation. See, there's an equal sign. Derivatives are involved, x double prime. And we want to come up with our function x. Now let's do a very simple case. Let's suppose alpha equals 1. So if alpha equals 1, you have x double prime equals minus x. Can you think of any function that when you take the second derivative of that, gets you the negative of what you started with? Has there been any hints, or has there been any sign of a function so far that we've talked about, so that when you take the second derivative, you get the negative of what you started with? Yeah, sines or cosines, right? So, what does that tell us? It tells us that if we follow Hooke's law, then we look like some combination of a sine function and a cosine function. So what does that tell us? It tells us that springs, when we release them and they go up and down, and imagine that simultaneously time moved. Of course, this is not the most compelling thing. I could just hold it in my hand and walk. If you followed the bottom of the spring, what curve would you trace out? It's basically a sine curve. Is that a coincidence? No, it's Hooke's law. Hooke's law tells you there's a differential equation. You solve the differential equation. In this case, we solved by guessing. Never underestimate the value of a good guess. Solve by guessing and say, hey, springs look like sines and cosines. So that's a very simple example. Now, unfortunately, guessing only gets you so far. So we're going to go and do some special cases. Now, we have done a really special case for a differential equation, namely antiderivative. So that's this side over here. So you see a y prime equals f of x. There's a derivative, there's an equation, and we have an initial condition. So we could just make up a problem. Does anyone have a favorite antiderivative problem they'd like to solve? If not, I'll just write one. What? You want to take the antiderivative of arctan? That's a Calc 2 kind of problem. To get to arctan. Okay, so 1 over x squared plus 1 minus 4x. And y of 0 equals 4. Suppose you have this problem. All right. So the goal, recover the function. In other words, solve for y. Can we solve for y here? What do we do? Well, we find the antiderivative. What's the antiderivative of 1 over x squared plus 1 minus 4x? Arctan. What? Oh my gosh. Who would have guessed we would have got an arctan? What are the odds? 2x squared. Right? You add 1 to the power. So this minus 4x is 4x to the power 1. 1 plus 1 is 2. So you divide by 2. Anything else? Plus c. So that's plus c. That's why we have this extra piece here. How do you solve for c? Plug 0 in. 4 equals arctangent of 0 minus 2 times 0 squared plus c. What does that tell us? Tells us what c is. Tells us what c is. What is c? Four. Because arctangent of 0 is 0. 2 times 0 squared is 0. So c is 4. It's not always that straightforward. Sometimes it is. Enjoy it when it is. So y equals arctangent of x minus 2x squared plus 4. So this is the kind of differential equation we've already been doing. But that's when we have y prime equals function of x. The thing is, we might have something more complicated. We might have something where there's not just x's, there's also y's. So we're going to look at a very nice case, which is what's called separable differential equations. Now, the name gives it away. When you see the word separable, what does that remind you of? Separate. So separable differential equations are differential equations where we have some ability to somehow separate something. Well, what we're going to be separating are variables. So we have two variables. Often they're y and x, but there's nothing special about y and x. We can use any two variables we want. And we say, look, we want to solve for just y, the original function y. So we have y prime equals some function of x times some function of y. So 3 steps. It's a 3-step process. So we'll go through and do it with the particular problem. So here we have a problem. Find y given y prime is 3x squared e to the minus y and y of 2 equals 0. Any guesses before we start what the answer is to that problem? Cool. That's okay. That's why we're learning the process. Okay, so step 1. We're going to separate. Now to separate says we're going to move it so there's just y's on one side, just x is on the other side. Now, we're cheating a little bit. Actually, we're cheating a lot of bit, but it's an okay cheat to do. The cheat is dy over dx is not actually dy and dx as separate objects. Dy over dx is just a notation for one thing. Our cheat is we're going to think like they're different things. But the good thing is notationally it's wrong, but procedurally it's right. And it makes sense to do it this way. So we're going to go with what procedurally is correct and helps us get the right answer. So that's what we're doing. So we're thinking of y prime as a fraction, dy dx as separable things. So we're going to multiply the dx across, divide the g of y across. So in our problem, we have y prime equals 3x squared e to the minus y. Y prime, we say, hey, that's dy over dx. What's another way to write e to the minus y? So with an e to the y downstairs. So that minus means it came from the downstairs. Okay, so separate. Let's put all the y stuff on the left-hand side. What do we have? So you move the stuff with y's across. On the left-hand side, we get e to the y dy equals, move the x stuff, 3x squared dx. Okay, that's step one. Separate. We've now separated, so there's only y's on one side, only x's on the other side. If you can't do that, it's not separable. If you can, it is separable. So this is sort of the ultimate test. Can you make it look like that? Now, here's the fun part. Now that you've gone to this stage, step one is complete. Step two, integrate. So we're now going to integrate both sides. And after you integrate, remember you're going to need a plus c. You only need one plus c. You don't need to have each side gets its own plus c. So, because constants get absorbed. So you only need one constant. What's the integral of e to the y dy? E to the y. It's a very nice function. E to the y, very resilient. So it's the derivative of e to the y is e to the y. The integral of e to the y is e to the y plus the constant. What's the integral of 3x squared dx? X cubed. And don't forget you need a constant somewhere, so you put it on the side with the c. Okay, so we're 2/3 the ways done. We separated, we integrated. The last thing is to uncomplicate. Now that's not a real word, but I chose it because it just sounded cool to say separate, integrate, uncomplicate. You know, it's the 8-8-8 kind of method. Has a nice flow. Separate, integrate, uncomplicate. Yes. Separate, integrate, uncomplicate. Yes? All right. So what does uncomplicate mean? Well, that means you're going to solve for c, solve for y. Now the question is, you may not have to solve for c. You may just leave it in general, but you may. When do you solve for c? The answer is whenever it's convenient. So we say, okay, is now a convenient time to solve for c? In other words, if we plug in our conditions, do we get nice numbers to play with? Yeah, we get nice numbers. Now let's talk about our initial condition. Let's read this. Y of 2 equals 0. What does that translate into? What is our initial condition? What value equals what? So there's an x and there's a y. X equals 2, y equals 0. So when we plug in our initial conditions, e to the 0 equals 2 cubed plus c. 1 equals 8 plus c. Ah, someone had cracked this code. 1 equals 8 plus c. So what is c? C is -7. So we have e to the y equals x cubed minus 7. Now, are we done? And why not? Yeah, we're not done because the problem was very clear. It said, look, find y. That was the first thing it said, find y, which means you have to get y by itself. One single y. One y to rule them all. So, currently the y is trapped inside the exponential function, so we need to free it. How do we get things outside of exponential functions? Logs, yeah, natural logs, ln. So if we take the natural log of both sides, natural log of e to the y, natural log x cubed minus 7, well, natural log of e to the y gives us y. So y equals natural log of x cubed minus 7. And now we didn't have to guess. You may have remembered a few minutes ago I said, hey, does anybody see what it is? Well, it wasn't so obvious. I don't think we could have looked and said, oh yeah, that's the natural log of x cubed minus 7. What? No, that's not obvious at all. But the process helped us. Okay, so remember, separate, move all the y's to one side, all the x's to the other, integrate both sides, solve for c and y. That's our procedure. All right. Now, are we going to learn other differential equations besides what we talked about today so far? Not in this class. So if you see a differential equation problem, it's going to be separable. And you're probably like, well, what if I want to learn other differential equations? I have good news. You have a whole course coming up, depending on your major. So any questions? All right. Let's try another problem. Find y, given that y prime equals x, I know that's a terrible looking x, but that is an x, over 2y plus 4, and y of square root of 7 equals 0. Okay, so let's go through our procedure. First off, it is a differential equation because we see it of y prime and an equal sign. So, okay, differential equation, and we see stuff involving x and y, so it's not an antiderivative problem, it's one of these separable problems. So, step 1 is to do what? Separate. Okay, so we look at it and say, hey, this looks like dy over dx is x over 2y plus 4. So, here, separation is going to be no big surprises. It's a lot like cross multiplication. Because it will be cross multiplication. So, 2y plus 4 dy is x dx. So that's step 1. We're a third of the way done. Now that doesn't mean we got a third of the points, but probably we got a couple points. Now what? Integrate. We're going to integrate both sides. What's the integral of 2y plus 4 dy? Y squared plus 4y. Nice. How about the integral of x dx? Half x squared? Is that true? That's true. Anything else we need to write down?
C.
Plus c. All right. Good. Well, we need to find y, which means we need to solve for y. And we have an initial condition. So if they ever give you an initial condition, this means you have to solve for c. So initial condition means solve for c. So, which one do you want to do first?
Solve for C.
You should solve for c if it's convenient. Let's find out if it's convenient. Our initial condition says what? What's our x value and what's our y value? X equals square root of 7, y equals 0. Y equals 0 looks very convenient right now. So 0 squared plus 0, 0, square root of 7 squared is 7. So that's 7 over 2 plus c. So what is c? negative 7/2. So we have y squared plus 4y is equal to 1/2 x squared minus 7/2. Cool. Okay. Well, now what? Are we done? Now we solve for y! Yes! Aha! Woohoo! We're going to solve for y today. We're going to solve for y. Hooray! Hip hip ha ha! Woohoo! Hooray! So, now there's a small snag in the solve for y plan. How many y's do we see? 2 of them. Oh, that's not the right number of y's. We don't want 2 y's. We want to get to 1 y. Okay, so we have to have a plan. How can we get down to 1 single y? Any thoughts? Any thoughts at all? Any ideas on what we should do?
Because then it'd be y times y plus 4.
Want a factor? So y times y plus 4? Then what do we do? Any thoughts on what we can do here? Oh, we could complete the square. Yes, that sounds like a great idea. Let's complete the square. Okay, all right. Well, in other words, it would be really cool if we could write that thing as something squared. Because then there'd just be 1 y on the inside. And like 1 y is a really nice thing for us. So we'll write down y squared plus 4y. And then we're going to have a suspicious gap here. Equals 1/2 x squared minus 7/2. The question is, what do you put in here to complete the square? Ah, good old completing the square. It felt like just yesterday. 4?
Wait.
Not 4? 4. You're confident.
2 times 2, and then they have...
Yeah, you're right, it's 4. Add 4. Where did that 4 come from? Middle term, divide by 2. So 4 divided by 2 is 2. And then you square it. Now, can I just add 4 like that? No, I can't just add 4 unless I do something which is equivalent somewhere else. So let's add 4 on the other side. So we get y plus 2, quantity squared, because we completed the square. That's 1/2 x squared. Now, minus 7/2 plus 4, is there another name for that? 1/2. Okay, so now there's just 1 y. Ah, the end is near. The end is in sight. We can see it. We can taste victory. Well, let's see what happens. So if you want to solve for y, what comes next? Take the square root, both sides. But if you take a square root, there's 2 possibilities. Plus or minus. Now what? Subtract 2. So we get y equals negative 2 plus or minus the square root 1/2 x squared plus 1/2. Now, is this our answer, and why not? There's 2 questions. Is this our answer? No. Very good. Why not? Because there's more space on the page? Well, kind of, yes. There is certainly more space on the page. How many functions have we written down? We've written down 2 functions. We were after 1 function. So the question is, which function are we after? Is it the negative 2 plus, or is it the negative 2 minus? Now, one of these is the right answer, one of these is not. Which one is the right answer?
Oh yeah, positive because the other one.
Now, how can we get a tie break going on here? Both of these satisfy the differential equation. So what's the tiebreaker? Plug in the initial condition. Now, if I take negative 2 and subtract something, can I get back to 0? No. It's really hard to take negative 2, subtract something, and get 0. So that's not going to work. So the initial condition helps us figure out which one we should pick. So it's negative 2 plus something. That gets us back to 0. So be slightly careful. This is a slightly trickier one. But, you know, it's good to see the challenging ones now rather than on the exam. All right. Any questions? Well, in that case, here's another one. Taken from an exam from a few years ago. Find y of x, given that dy dx is y squared cosine of x minus 2xy squared, and y of 0 equals 1. Okay, so the process, you separate, you can pull the y squared out. The y squared comes across as y to the minus 2. Integral of y to the minus 2 is y to the minus 1 divided by negative 1. So there's a negative 1 over y. The integral of cosine minus 2x sine x minus x squared. There's a plus c. You can solve for c. Then you just move the negative across and flip, or other way around. So there's our answer. Beautiful problem. Beautiful problem. Okay, so in the time remaining, I want to read one more problem, because this is one that I wrote many years ago. And sometimes in your life, you write a problem and be like, this is it. This is the problem I want written on my tombstone. This is how I want to be remembered. And then I realize it's going to be a very, very, very big tombstone if they write this on my tombstone. All right. So let me read the problem. You might recognize certain aspects of this problem. Now the star-belly sneetches had bellies with stars. The plain-belly sneetches had none upon theirs. Then one day Sylvester McMonkey McBean came to town with his wondrously wonderful machine. Just one pass through, hop on board, and you will have a star for sure. The sneetches listened, and the sneetches thought. And those who wanted a star-belly stepped up and bought. Sylvester kept track of the proportion, P, of sneetches with stars after T months, and noticed, as people often do, that P prime is 1/3 T times 1 minus P squared. His business was quick. He did not want to delay, and so he recalled on his very first day that P of 0 equals 1/4. To make a quick buck and then leave this place, he decides to leave when P equals 3/4. How many months will it take until Sylvester McMonkey McBean leaves this place? That's the problem. Now, in the interest of time, because I know we don't want to dwell too long, there's a lot of words. How many words do you have to pay attention to? Almost none of the words, right? You have to, no, the words give a wonderful background. By the way, does anybody recognize this story? I didn't come up with this. Dr. Seuss. Yeah. So you pay attention. When you're doing a word problem, what should you look for? Non-word stuff. And you're like, oh, that's not a word, that's not words, and that's not words. And oftentimes you're like, hey, I'm just solving a differential equation with an initial condition, and then I want to find the time t that satisfies that. Well, it's easier than it sounds. So in the interest of time, I wrote up the solution. So here's our differential equation. We separate and integrate, plug in the initial condition, and here is an expression. Now, you might notice something. I did not solve for p. The question doesn't ask me to solve for p. I don't have to solve for p. I have to find t. So that's what my goal is. Not everything requires you to solve for p. So we know p of t, we want that to be 3/4, so we plug in 3/4, and it turns out that t squared should be 16, so 4 months. Sylvester McMonkey McBean will be gone in 4 months.